Hello and welcome to NASA's Goddard Space Flight Center. My name is Michelle Thaller and we have a wonderful honor today of presenting a scientific colloquium about some amazing new results having to do with the end of the dinosaurs. This is something where space science and earth science come together and shows you how very much enmeshed all of these different types of study are. So we're honored today to have Robert DePalma talking to us, and he'll be giving this colloquium. Now, Robert, it turns out, is a doctoral candidate. He'll be very soon getting a doctorate, I hope, from the University of Manchester. Is that correct, Robert? Yes?
Well, Michelle, thank you so much. It's an honor to be here today. I will be getting a doctorate very soon from University of Manchester, and I'm on the faculty at Florida Atlantic University.
And you introduced yourself to me as a vertebrate paleontologist, and you specialize in the end of the Cretaceous period, which was ended very suddenly by an event that we're going to talk about today.
Absolutely right.
Okay, well, enjoy the symposium. We'll be back later. Thank you.
Thank you very much. And today I'll be talking about a very, very exciting bit of research that deals with probably one of the worst days of the Mesozoic. It's when the Cretaceous ended, and anything that would have experienced that day would have had probably the worst day that it ever experienced. That is, of course, the Chicxulub impact event. And that event is what set in motion a series of events that really changed the topography of life on Earth as we know it. And it set the stage for what we have today. The important thing to remember, though, is that the Chicxulub event and understanding the Chicxulub event in every detail possible is literally our window into the past to understand how biota is going to respond to impact events, how biota is going to respond to global scale hazards, and in turn, how can we possibly deal with that today? So it directly relates to what's going on today, and that's where Earth and space science really meet. And a little bit about the Chicxulub impact. We're talking about an asteroid that was relatively 10 kilometers in diameter, and it's going to come in roughly 20 kilometers a second. It's going to release enormous amounts of energy. You're going to have seismicity, possibly magnitude 11 to magnitude 12 at the impact site, and that's greater than you're going to see in the Earth normally. And what that did is that set in motion a cascade effect of ecological collapse. You're going to block out the sun. You're going to have this injection of a massive amount of contamination into the atmosphere. And it's really going to set everything off kilter. That is what set in motion the massive extinction that basically took out 75% of species on Earth. So all of that we know, we've got this tremendous amount of information about the KPG event. And there's still questions that are unanswered. We know all sorts of things about what happened on these long time scales, talking in generalities. So what happened over millions of years? You know, what's our percentage of species that died? And what happened on a large scale? But what about those finer time scales? What happened in the hour to day time scales? And the fact of the matter is, we just don't know the answers to a lot of those questions, because the way to answer them depends on a geologic record that is suited to answering those questions. Most of your rock units don't preserve that sort of data, and it takes a really special sort of an area, special sort of a site to preserve that kind of a snapshot. And that's where this new site comes in. So there's actually a new site at the very end of the Cretaceous in North America that preserves a snapshot of life on Earth. And this site, it gives a very, very tight view of what happened in the terrestrial setting. It gives a view of what happened moments after impact. We're able to see what happened with the very first stages of ejecta accretion, and we're basically able to see, well, what did happen in that little tiny nugget of time that really is sort of missing in the geologic record now. How can we actually fill that? And the site actually does that for us. The study region is within the Hell Creek Formation. So that represents roughly the last 1.3 million years of the Cretaceous. It's a terrestrial setting, sort of like the Gulf coastal plains today. You had all these rivers that would have flowed from the inland areas all the way out to the seaway that would have split the US in two back then. You had all these fluvial deposits. You had lots of dinosaurs. Life was abundant. This was a vibrant, thriving ecosystem in the Hell Creek. And it's a hotbed for KPG research, because it just happens that this area is the best terrestrial succession of Cretaceous to Paleogene rocks in the world. And we're able to study the impact event. Most places that is just preserved as a single layer of fallout, but the new site actually has something a little bit different in store. Normally we see the KPG boundary as something like this. There I am up on the outcrop studying the dividing line between the Cretaceous and Paleogene. there's a closer view. There's Professor Phil Manning and I digging into it, and you can see that that layer is very, very distinct. You've got your dark gray sediments and this beautiful light-colored, this peach-colored clay layer. And that clay layer is 100% composed of impact-derived materials. You've got shocked quartz, you've got ejectospherules, you've got an iridium spike, you've got all this stuff that was blasted into the air, and it came down around the entire globe as this little layer. And this is how it manifests in the Hell Creek Formation. We've heard about the impact event. We've heard about the Chicxulub impact, and we know the name Walter Alvarez that's associated with it. And here we are actually digging into the layer at the site and working through these problems at this new site. And it's sort of an incredible story as it comes together with all the minds that are involved and piecing these little details together. So let's get into the site itself. The site is known as Tanis. And this site, the depositional setting, is basically in a little river environment back in the Cretaceous. So you have point bars in the bends in the river, and essentially what occurred is a massive surge of water left a layer of mud as a drape over one of these point bars. And you've got maybe 10.5 meters of elevation change, so it's a pretty steep point bar. And you've got this veneer of sediment that got deposited really rapidly on the point bar. It's actually really good for preservation. And you can see here, it was a really turbulent deposit. You've got all of these chaotically deposited laminae of silt and sand, and mixed in with that, you've got this mass death layer of mostly fish, and you've got trees, you've got other plants, you've got other organisms, all mixed in to this really dense layer of dead creatures. And this was all pushed in at relatively the same time. And you can see it right, the chaotically oriented mud clasts at the bottom. So what those are, we call them rip-up clasts. And then when you have a really turbulent surge of water, it's going to rip up whatever sediment it encounters. It's going to basically roil those together. It's going to tumble those and cause this little layer of rip-up clasts. And that's what we see there. We have our sturgeon there, and that's mostly what we see with the fish. We've got sturgeon and paddlefish. And then mixed in with those, we've got other terrestrial biota. This is what the site looks like today. It looks very, very different. You don't have that subtropical area that you would have had in the Hell Creek Formation. This is the prairie in the American West. And you can actually kind of get an idea of the elevation change there at the site. We're about 2/3 up that angled point bar. And you can see way down there at the vehicles is near the base of the point bar. And it even goes up from there. We've got 10.5 meters of elevation change continuously unbroken in that deposit. And when we start digging up these remains, you got to think, well, when are we? You know, we're basically digging through time. So when are we? That's the big question we always ask. And we have to answer that multiple different ways, not just one. And one of those ways is with the plants. So the megaflora at the site. And this is one of the things that has been independently verified by paleobotanist Patrick Herendeen. And when we look at the flora that are present in that point bar deposit and the surge deposit, and compare that to the underlying sediments that river dug through, the incised sediments, which are obviously older, we see a distinct difference in the flora between those. The flora that are in the surge deposit and that are in the point bar are much younger, and they constrain to the very, very uppermost Cretaceous, the terminal Cretaceous, and the uppermost Hell Creek Formation. Same with the pollen. And this has been independently verified by paleontologist Steve Bozarth. And the pollen shows us the same thing pretty much that the flora show us. Basically, the pollen in the uppermost part of the deposit, in your point bar and in your surge deposit, match with the uppermost Hell Creek, the terminal Cretaceous. And then the incised bedrock is a little bit older. It's what you would expect. So we've got these redundant ways of basically putting a timestamp on our deposit. And the ejecta does that as well. And here are some examples of the ejecta. Here we've got the space component of this site. And this is a basic stratigraphic column of the site. You can see the grain size curve. So you go from large to small grain. We've got two major pulses in the site. So we've got one major pulse, backflow, and then another pulse that goes all the way up. There's ejecta throughout this deposit. You've got ejectospherules, like you see here, that would have come from the impact site. You've got that impactor, it hits your target rock, and you get blobs of molten glass and different material that shoot up into the sky, out of the atmosphere, and they come back down again. And that is a diagnostic feature of impact, as is your shocked quartz at right, which we find in the capping KPG Tonstein, which capped the site. So you literally have this ejecta-bearing deposit, which is capped by the very fine-grained debris from that impact event. So that really seals it all together. You also have microcrystites. So these are formed as a condensate from the vaporized impactors. So you've got that asteroid, it vaporizes on impact, and as that condenses, you get these forming. And you've got the typical enrichments in chromium and nickel and iron and so forth that are attributed to the microcrystites. Now, getting into all the stuff that's buried in the deposit, let's get to the coolest thing of all time, which is logs, right? Because we all think logs are really cool, right? Well, these logs actually happen to be cool because in this site, wrapped around the logs, you've got all these animals and different things, but the logs themselves, which in some cases can be 20 to 30 feet long, at the longest ones we've dug up so far, really well preserved, semi-three-dimensional, but they also have runnels of amber on them. So we know that resin would go down the trees, and we've got runnels of amber on the exterior of the logs. Okay, that's great. We've all seen Jurassic Park. We know that amber is a great thing for paleontology, but in this case, amber, when that resin is still flowing, is a way to capture whatever is going through the air. And on the day of the Chicxulub impact, that's the time when I really want to see what's in the amber. So what are we finding here? Well, we're sieving out the amber. We're actually going through it. There's Pim Kaskis, another researcher who is doing work out there from VU Amsterdam. And here are some of the pieces of amber from the site. There's little pieces of the wood, but here we've got pieces of amber from the site. You can actually see texture on the surface of that one that matches the bark from the trees. So this is really well preserved amber. And when we look inside, we've got beautifully preserved ejecta spherules from the impact event. Now, these haven't been exposed yet. They're still in the amber. And these two spherules have been exposed, and we can see that beautiful black glass of the impact spherule. That's not usually what you see with the Chicxulub impact. Normally, we're looking at what you see at left, a really awful, crumbly clay spherule, because a really bad thing happens in the geologic record. What happens is glass will then alter when it takes on water. So it hydrates, and glass will then turn to clay, in this case, smectite clay. And it becomes crumbly and not too nice. And we look at these as researchers of the impact event, and we think, oh man, what did that look like on the day of impact? What did it look like when it was pristine? And we have to use our imaginations to think, what did that used to look like? That's what it used to look like. That's one of the only pristine pieces of impact ejecta from the Chicxulub impact. And the amber there is full of it. So that's a really good hotbed for research, and it helps us to give a fingerprint to the site, right? So some of those little clay spherules didn't completely alter. So this is a beautiful micro CT that my colleague Lauren Gertschy put together. And the blue portion is the clay, all right? And the interior, the green portion, is the unaltered core of that spherule. And looking at those and the ones from amber, we're able to establish a geochemical fingerprint with the Chicxulub impact and with glass from the Chicxulub impact from elsewhere and geochemical fingerprints from the crater site. And also that glass has a temporal fingerprint. So we're able to radiometrically date that, argon-argon dating, and come up with a date that matches the Chicxulub event. So we're able to match this event with the site, with the biota, with the microorganisms, with the geochemistry, with the radioisotopes, everything. So we're able to come up with these reinforcing ways of linking it with the Chicxulub event. So good, we've got something that's linked to the day of the impact. That's excellent. So how can we get this timing constrained a little bit? And the ejecta sort of is our key, because that entire column of sediment was getting deposited during active ejecta accretion of coarse-grained ejecta. So basically, since that site is covered in your fine-grained tonstein, that came out later, and your column is filled with your coarse-grained ejecta, you're tied to that coarse-grained ejecta accretion time window. And that's within roughly the first hour, maybe two at most after impact. You want to be really, really generous, maybe say an hour and a half to 2 hours after impact. And geologically speaking, that is the blink of an eye. That is the sort of honey spot that we're looking for. Because when you're looking at the impact event in the terms of hundreds of thousands to millions of years, and you're able to get a site with that sort of temporal resolution, then you can answer all sorts of questions if you find the right types of material there. And that we know we're in the gold now. Now is when we can start answering those questions. Now, go back to the temporal resolution. How can we possibly constrain that a little more? The ejecta is our key. We know that whole deposit was within the first hour or two after impact, but when we have lenses like that throughout the deposit, we can work out, based on their average diameter, when they would have arrived at the site. And Walter actually helped by doing a lot of those calculations, and what we turned up with is you can get those different lenses throughout the thing, and those are basically your little timestamps throughout the deposit. You could further subdivide the chronology of this deposit based on the incoming time of the ejected spherules. And that's the beauty of the site. So you can actually get this little tidbit of a view every step up the column. But that doesn't actually solve, the surge. Where did the surge come from? I'm not going to belabor that too much. But we have this big surge of water. It happened at the same time of the impact. Where did it come from? What's the deal? Basically, we know that the site was part of the point bar system of a big river, a very large river that cut deeply into the Hell Creek landscape, and that emptied out into the Western Interior Seaway. Okay, we already know that fact. We know there was a big surge. It occurred in a couple of pulses. We got bidirectional flow preserved in our sedimentary structures. Most of our surge was going inland. Essentially, that river was flowing backwards during the greatest sedimentation episodes of that event. So we know that surge came from the direction of the Western Interior Seaway. It was flowing westward from an eastern direction. And that's kind of like a tip-off right there. It's a tsunami-like wave. And it's turning out that the seismic waves arrived right around the time of this wave that deposited the Tanis sediments. So probably the seismic input was what caused it, not a tsunami from the impact site, but it's a seismic shaking. We're not going to get into that too much with this one. But basically, this is what your cross-section would look like, an idealized cross-section of the site. Your white arrow out is going to give your flow of the river, easily documentable at the site. You've got all your typical SED structures. And then you've got your opposite flow from the surge. Would have been about 10.5 meters, and it would have filled it up like that, possibly more, but that's what the fossil record shows us. And it could have been even deeper than that. We've got, let's go back a little bit. We've got KPG boundary preserved directly on top of the surge deposit here. We've got KPG boundary preserved here in the Overbank deposit, and then also at the edge over at 6 at Brook Butte, which is about 1.1, 1.2 kilometers to the north. So we've got KPG boundary sediments all over the place from the site. And there it is filling up. And we've actually got some of our marine fossils that show you, yes, this is probably a surge that originated from the seaway. We've got freshwater organisms at right, like the sturgeon. We've got this beautiful feather, which came from probably a bird or a maniraptoran dinosaur. We've got those mixed in with ammonites. It's a marine shelled mollusk. We've got sharks, mosasaurs, different marine fish, marine foraminifera, and things that just don't belong there. These don't exist in the Hell Creek Formation normally. There are 2 marine tongues in the Hell Creek Formation, but the fossils, the timing, and the mode of preservation don't match with the site, so there's no linkage there. So we'll talk about the animals a little bit, the biota of Tanis, and the new insight into life at the end of the Cretaceous based on that. So we've got our connection between the impact event and the biota. And most of that biota turns out to be fish in this case. We've got a lot of, we got sturgeon, we've got paddlefish, we've got at least 3 new species of fish that are unnamed at this point, so we're already learning about the types of organisms that existed back then. But we're going to talk about a little more interesting things here now, the pterosaurs. So these are winged reptiles, these are flying reptiles. They existed back then at the end of the Cretaceous. The Hell Creek Formation had only one type that we're aware of, the asdarchids. That's the giant type. Quetzalcoatlus is one of the ones that's more well known. It's the size of a small aircraft. So these are big pterosaurs. They're well known around the world. This is a cladogram of the basics of our knowledge of pterosaurs from their origin all the way up to the extinction. We know a lot about pterosaurs. We've got plentiful remains, and they're sort of like one of the favorite things to study. The one thing we don't know a lot about is what were their eggs, babies, reproductive strategies, and et cetera. The embryos are practically unknown. That is the temporal span of our knowledge on pterosaur embryos. Not that much. We've got one pterodactyl embryo. There are 18 embryos for the ornithochirids. That's it, you know, that's all there is in the entire world, and none of them from North America. The good part about the site is the preservation potential is so good because of that rapid deposition that we are able to add a data point to that and add the Asdarchids to the end of the Cretaceous. So we expand this temporally and taxonomically, which delights us to no end. So stratigraphically, this is where we are. Most of our carcass tangle is going to be down here at the upper part of the first surge pulse and the lower part of the second pulse. That's where most of the organisms are in this deposit, although, as I mentioned, some cross-cut the entire deposit at an angle to the bedding planes. So there's stuff throughout. That's just your main concentration. The deposit's capped by your KPG tonsteins, so you've got your pristine, uninterrupted layer of impact debris. And the embryo comes from right here within the upper 2/3 of the deposit. And here it is. So at left, you have a view. It's about the size of a hen's egg. This is a plain light view of the embryo. We can see the tangle of dark brown bones there, which I'll show you later are nicely articulated in most cases. A brown halo for the shell, and it compares favorably with the embryos that are found elsewhere. So at right is one of the more famous embryos from Asia, and it's a beautiful ornithochirid embryo. And the mode of preservation and the style of folding is very, very reminiscent of the Asian one when we look at the Tanis one. And here's a shot that Dave Berman and I got going with the laser-stimulated fluorescence, and you can see the bones come out, and you can actually see some of the articulation. So here you go, you've got your upper arm bone, your humerus, and you've got your radius and ulna, and then the long wing elements that are preserved there. They don't match anything that should be there. They don't match the birds or the dinosaurs, and the structure of the bones and the anatomy of this creature really only compares favorably with the pterosaurs. So we're relatively confident, and so is Dave Unwin, our co-author, one of the world's experts in pterosaurs, that this is a beautiful Asdarchid pterosaur embryo. And so, as scientists, we just have to keep picking away at the details and figuring out what we could find out. And with these samples, and with the ejecta, we ended up going to two of the most powerful synchrotron facilities in the world. We went to SSRL at Stanford University and the Diamond Light Source in Oxford, UK, two absolutely gorgeous facilities, and I cannot say enough about how wonderful they were during the analytical procedures. Here we are at the beamline, scanning the specimens. We've got the beam pipe here coming out of the storage ring, giving us our lethal synchrotron radiation. You don't want to be in there when it's operating. And we're able to find details with these methods about the organisms and their chemical makeup that you just can't find otherwise. And this particular beamline enables us to look at the chemical makeup and the spatial distribution of those different chemicals at a molecular scale. And you're able to see, what is that organism made of? Is that material organically bound, or is it something that's an artifact of the fossilization process? And we're able to take these things down and look at all these little things that normally you can't see. And in this case, it's the sulfur. So there's a blown up view of the egg. Blue, you're looking at the bones of the pterosaur. All of that yellow is sulfur, and the sulfur follows the outline of your eggshell. The sulfur in this case is not just sulfur. We'd be happy if it was just sulfur, but in this case it's not. Through the X-ray absorption spectroscopy, we're able to determine that all of the sulfur you see on the screen was organically bound. That is not sulfur that's a result of the fossilization process. It's not something that precipitated or something during the lithification of the outcrop. This is something that is tied to the organism itself. Moreover, it's probably tied to the eggshell, because you would have had organic sulfur associated with the whole organism, but the eggshell would have been a little bit more resilient. And we suspect that that sulfur is probably tied to the cysteine in the eggshell proteins. And we're going to be looking further into that. Going on to the shell, here's some SEM shots of the shell. And it turns out it's actually a dual-layered shell. This is a top-down view. And here you can actually see where at the edge of the shell, there was a little bit of a flake-up that occurred. And you can see there's the upper unit of the shell, and down below is revealed your lower unit of shell. And that basically shows us a difference in texture, a difference in composition. And you look a little bit closer, you can get a closer view of the upper unit of the shell, top down. And there it is actually compared to a soft-shelled gecko egg, modern day. And you can see them compared side by side, somewhat similar to each other. You look at them edge on, and you can get a little bit of a better view. This is sort of an oblique top-down view. You can see that flaked edge there. And there's a direct cross-section where you can see a beautiful distinction between the upper and lower layers, both in color and texture. And that's even more illustrated by the SEM images, because you can see sort of this haphazard, grainy texture of the upper unit. In the lower unit, you could even see little reminiscent structures of the sort of parallel bedded structure that would have been there, sort of like the laminated structure. And when you look at the SEM and the elemental difference between the upper and lower layers, the textural difference, it actually compares very favorably to the modern eggshell there as well. That's a soft-shelled snake egg, modern day. And as we went through this specimen, we saw more and more features that signified that this had a soft-shelled egg, similar to the early pterosaurs. But now we know that that feature existed into the latest Cretaceous, which no one knew until now. And here we go. All right. This is another beautiful view of the skeleton. So this is a zoomed-in view. We can see the shell is outlined in zinc. We've got strontium outlining the bones. And the one thing to remember here is that the bones of this are really well ossified. They're well preserved, well ossified. This was probably a late-term embryo based on how many of the bones were ossified, based on the articulation, based on the size. Probably was a late-term embryo. And when you see that much ossification occurring late term, that probably is an indication that it would have been better able to fend for itself once it hatched. It probably was not going to be helpless once it hatched. And when looking at some of the dimensions provided by other studies, this is where ours plots in. Naish et al. Did a beautiful study on precociality in pterosaurs recently. And the Tanis embryo, some of the arm dimensions of that embryo actually plots very close to the embryonic pterosaurs, or hatchling pterosaurs rather, and sort of close to the trend line for the non-hatchling pterosaurs as well. So long story short, some of the preliminary data about the wings shows us that it is at least compatible with other pterosaur specimens that would have been capable of flight. So this probably would have been a precocial organism. And that's a good advantage, especially if you're going to be in an area where things want to eat you. And that's how big the thing would have been when it was hatched. So this is the first reconstruction based on the fossil, and this shows the articulated reconstructed skeleton. The bones that were not present in the original were reconstructed based on the proportions of Asdarchid pterosaurs, but we had representatives of a lot of these bones, so it is a faithful reproduction of how it would have looked if it got to hatch. A little bit skinnier than if it hatched. But it would have been basically the size of a bat when it hatched. So pterosaurs, wonderful. Dinosaurs are even better, I think, maybe. I think they're on par with each other personally. So let's talk about the Dinosauria from the deposit. Back to our trusty column. We already have our KPG boundary clay there. We've got our main concentration of fossils down there. Where do the Dinosauria occur in the deposit? That's something we really haven't gotten into much yet. Two places. First, we've got actual dinosaurian remains in the deposit, and the ones we're going to talk about here come from right about there in upper unit 1, at the very top of the very first surge pulse. And then we've got a very cool thing that occurs. We've got trace fossils in the paleosurface right under Tanis. So essentially, when you've got this surge that came in and covered that riverbank and covered that point bar, it covered the active paleosurface of the latest Cretaceous. Whatever was there got covered. And in this case, we had footprints in that paleosurface that got covered by a beautiful contiguous layer of sediment. These were not older footprints that were re-exposed. These are not footprints that had formed any other way. This is latest Cretaceous material. And here's how that shakes out. So at right, you can actually see this beautiful angled paleosurface. You can actually see the angle of that point bar. And this is the exposed surface. You can see it's trampled all over the place. It's not smooth. It's like a game trail. It's almost like you go to a cow ranch or something today. And then that is directly overlain by that veneer of the surge deposit. Very different lithology. And the basal sands of that surge deposit fill all of those tracks and footprints, and totally different sedimentation. And when that dries just a little bit in the sun, it just pops right off, and you've got all of the beautiful tracks beneath. And here we've got some of them. There's a three-toed track from one of the dinosaurs, and we've got the surge deposit resting right on top. And, you know, what's the timeline of this? You know, what we argue is this is probably not too long before impact. Not directly before impact. If it was the same day, it would have been a muddy deposit, and your surge would have washed that away. If it was too long before the impact, in this subtropical environment that would have been raining all the time, those would not have lasted well in the record. So basically, they would have left these tracks in the mud. The mud would have dried for long enough that they would not have been washed away by the surge, but it wouldn't have been too long. So we're talking, you know, weeks to months probably. And here are some of those beautiful tracks. Theropod dinosaur tracks. Those are the carnivorous dinosaurs. Dave Burnham's hand for scale next to that beautiful tridactyl print there. We've got ornithomimid over there. So we've got the meat eaters represented. These are probably from herbivorous dinosaurs, but they're not yet determined which taxa they're from. But you know, the fact of the matter is we've got a diverse assortment of dinosaurs. So we don't necessarily have to identify the specific taxa right now. We've got to identify morphotypes, and that gives us an idea of species richness. You know, how rich were the dinosaurs right at the end? This gives us a very good idea. Not only that, we also have infant dinosaur tracks. So infant hadrosaur, and we've got infant either Ceratopsian or it could possibly be mammal, but it's probably Ceratopsian based on the Manus prints. And when you look at the scale, these things are about the size of a silver dollar or a golf ball. Very, very small. That's from a baby that would be about that big, and that would have been from that year's breeding season. So those are babies from the last breeding season of the Cretaceous, and you know that they were living there not too long before the surge. So about the Triceratops, yes, they existed in the area, and yes, they died in the area as well. So while excavating into the surge deposit, we identified some soft tissue associated with those. So we already reported a partial hip from a Ceratopsian in that deposit and some soft tissue associated. Well, we wanted to go back and find more if there was more there, and more there was. Here's Riley Weir, one of the grad students at FAU, at initial contact with this beautiful scaly pattern from what we now know is Ceratopsian. At that point, we knew it was from a large dinosaur. And here we have Lauren Gertschy continuing that excavation, and this protuberance on the top of the very, very large scale, that is very similar to what you would see in Triceratops. I've not seen it in any other Ceratopsian personally. It's almost certainly from a Triceratops. We're like, oh, well, how much is actually there? We ended up getting lots of skin from this animal. We got a selection of bones, which shows us that we had an associated skeleton at one point in time. And that animal probably died right there. Probably was not transported in like we originally thought. With that many bones representing that much of the skeleton, you know, probably not transported in. But it died before the impact. This was not something that was part of the asteroid impact at the end. We had a lot of decay. The bones were disarticulated, and this animal probably died weeks to months before impact. Again, like with the trackways, you're not going to have this die years before impact because all that soft tissue would have been decayed away. You would not have had an opportunity to rework it, so it was not a fossil at that time and reworked. So we're looking at probably weeks to months before impact. So sadly, yeah, that was not something that died in the impact surge. But we did find something that probably was. So here's some of the new stuff. We've got Dave Burnham's thumb for scale next to soft tissue associated with bones that later turned out to be from a dinosaur. And after much digging, this is what the sediment looks like when you start. You know, it's really this awful mess, and you have to make sense of this, and you have to do a very detailed excavation. Over time, we ended up revealing a herbivorous dinosaur in that deposit. And here we are delineating the block with a herbivorous dinosaur. There's actually a palm frond over here, and we're delineating the creature. This is the outline of the rear leg. So we have the thigh going to the calf. We've got the gastrocnemius would have been there. We've got the ankle and the toes all the way down to the claws. And this animal was preserved in such a way that you had these three-dimensional skin impressions over the articulated skeleton, meaning this was not decayed prior to impact. It was not decayed prior to deposition. It was beautifully preserved. and we did not know exactly what it was. We know it was a herbivorous dinosaur. We narrowed it down. It's probably either from a Pachycephalosaur or a Thessalosaur. So those are two herbivorous dinosaurs, sort of like a gazelle ecomorph of the Hell Creek landscape. And they would have been gorgeous little creatures, but we weren't quite sure which type it was. So we dug deeper, figuratively speaking, and did some micro-CT work. These are micro-CTs, literally a digital dissection of this dinosaur. So this is like a dinosaur CSI. This is the beautifully articulated toe of that dinosaur inside the three-dimensional fossil skin envelope. So you've got all the digits of the toe. You've got the claw here. You've got the ankle. At right, you can see the leg partially flexed, and you can see some breaks in the leg that are from fossilization, but there are some green stick fractures in that. Those green stick fractures are from the time of death, before fossilization. So it actually had trauma before fossilization. And this turns out to be from a dinosaur called a Thessalosaurus. That's what this thing was from. And here we've got a compound fracture of the femur from before death, and we've got all these beautiful skin impressions. There we've got the top of the foot with these overlapping scutate scales like you'd see in a chicken or an ostrich foot today, just like that. And here we have it 66 million years old, preserved in this dinosaur that most likely experienced the worst day that a dinosaur ever could experience. That dinosaur probably witnessed the impact event in its own special way. That's also teaching us new things about Thessalosaurs, in addition to teaching us about the impact, because the scale patterns we're seeing on this leg are scale patterns we've never seen before in a herbivorous dinosaur. So we're able to actually reconstruct, better than before, the appearance of the leg of a Thessalosaur, because we've got these very elongated tubercular scales, which probably would have equated to some sort of a pattern of color or something like that in the animal. They at least would have been a texture pattern that would be visible on the animal, possibly a form of camouflage. No one knew they had that before. So because of the preservation here, we're actually able to determine new things about this dinosaur. And then we have to go through our list of our dino CSI. What caused the death of this thing? We don't want to jump to conclusions and say, yeah, this is something that was brought down by the impact. We're scientists. We want to figure out and weed out what is incompatible with what we're looking at. Predation. Could it have been preyed upon? Lots of herbivores are. In this case, it's not well supported by the fossil. We don't see tooth marks. We don't see anything that indicates that it was either partially or completely consumed. We don't see evidence that a predator engaged this animal or shed teeth of the predator. You see those sometimes too. We don't see that. How about disease? Was it disease? Could it have died right before impact, maybe a day before, a week before, a diseased animal? Well, Paul Barrett and other people actually have examined the specimen, and they agree with us that there's no obvious evidence of disease associated with the leg. It looks like it was an animal in good health. It looks like the animal probably was just a normal, average Thessalosaur, just living out its life. We don't see any obvious signs of a bad disease. So probably not disease. Okay, how about trauma? I just mentioned trauma. We do have trauma, yes. We've got green stick fractures. We've got fractures that occurred at the time or right around the time of death. Good, okay, that gives us a little bit of evidence there. And could this have been contemporaneous? It's compatible. Now, as a scientist, I'm not going to say yes, 100%, we do have an animal that died in the impact surge. Is it compatible? Absolutely. Because we've already weeded out some of the most obvious causes of death, and it's compatible that it could possibly, plausibly have been a victim of that impact surge. It did not decay before burial. That's one good point of evidence. So that is really kind of an exciting thing to think about. This creature could actually have experienced that event. This, rather than thinking, oh yeah, the impact caused all this extinction, you're thinking, wow, how did the impact affect the life of this single creature? And that brings it down to kind of like a human level. Now back to the impact itself, let's talk about what the impact tells us about the impact. The ejectaspherules, the beautiful ones that are totally preserved in glass, that are not altered at all into clay, have a little bit more to tell us. They're not just pretty, they actually have data to provide. This is the exterior. We actually still have some pieces of amber adhering to those. There's the interior. We see beautiful gas bubbles in there like we typically will see in the impact melt glass. I'm astounded at the beauty of the interior of this thing, because when you look at that glass, you can just imagine the day that it was flying through the air, out of the crater, out of the atmosphere, and solidifying, as this little piece of glass. But there's stuff in there that is really important to us as scientists, and that's the inclusions. We found bits of rocky debris in several of these that we're like, okay, just like you see an insect in amber, now we're seeing a piece of rock inside the glass, perfectly preserved. What's that going to tell us about the impact? There's a little nugget there. There are all these little dirty nuggets in there. Every single speck that takes away from this beautiful clear glass is a piece of debris. And that's essentially the equivalent of sending someone back in time with a sample vial to the point of impact, collecting a sample, bottling it up, and perfectly preserving it for scientists right now. And that's like research gold. So what we found is that almost all of these little unmelted nuggets are enriched in strontium and calcium, and they're parts of the carbonate platform of the Yucatan. They're part of that limestone platform that got hit and got thrown into the air. These are pieces that didn't melt all the way. You expect that. It's very cool, very amazing. For all intents and purposes, those are some of the best preserved pieces of the Yucatan platform that got hit, because they haven't been weathered in 66 million years. So you've got those little bits of evidence from the moment of impact, and it brings you kind of closer to, feeling like you were actually there on that day. You can picture these being encapsulated by the molten glass. But when we were at Diamond Light Source in Oxfordshire, we found a couple of these fragments were not quite what we expected. Two of the spherules had fragments in them that were wildly different in composition than those others. They were not enriched in the calcium and the strontium like we would have expected. These were enriched in the iron, they were enriched in chromium, they were enriched in nickel, and a few other things I'm not going to mention just yet. But these fragments matched what we would expect from elsewhere, not from Earth. And as we go through the microanalysis, we can demonstrate that further. This is an SEM view of one of those fragments. We actually have a chondrule, or what appears to be a chondrule, that is preserved within this brecciated matrix. And we have the dark region around the exterior, which is likely related to the fine-grained rim of the chondrule. We've got a closer view. That's a much better view of the chondrule, actually. We've got some chromite along the edge there. We've got a beautiful view of the brecciated matrix, really nicely formed chondrule, and probably olivine. Actually, it probably is. We've got enrichments of magnesium there. Beautiful brecciated matrix. We got chondrule, and this is our view of one of those fragments. So the microstructure is going to tell us a lot about where it came from, and you'll be able to do some of your mineralogy with your EDS data and such. And the ratios of those elements to each other tell you a lot about what these things are made of. And obviously, we don't jump to conclusions with these. We let the instruments tell us what they tell us, and the specimen will tell us what it is. So far, the data is showing us that our sample falls within this region, which is the carbonaceous chondrites. So most likely, this particular sample is allied with the carbonaceous chondrites. And that's good to know, because that actually falls in line with what Frank Kite was telling us years ago. Kite described this sample at Wright, which was found in the Pacific in a drill core, 9,000 kilometers from the site. That's like 3 times farther than Tanis. And it's a little larger than my fragment. It's about 2.5 millimeters. Don't know how a 2.5 millimeter fragment would have gotten that far, but assuming this is actually from the impactor, there is some data we can get from it. The problem is this: carbonaceous chondrites are not resilient. They're not nickel iron meteorites. They fall to hell in the environment. They hydrate, they alter, and this piece is no different. That particular specimen went through 66 million years of being ravaged by the ocean waters and the deep sea sediments. There's no original mineralogy that exists. There was a lot of chemical exchange with the exterior matrix, and there's no way really to tell exactly what type it is, except probably carbonaceous chondrite, and he proposed it's probably either a CV, CO, CR, or CM subtype carbonaceous chondrite. That's good. That's good to narrow it down a little bit further. But still, it doesn't really give us that final oomph. Do we really know what the asteroid was? And our current specimen falls within this region of the graph. And this is one of the many different analyses. I'm not going to bore you with all of them, but ours falls within that region, which identifies it as most probably a CM-type carbonaceous chondrite, which is excellent because that actually falls right within Frank Kite's range. There's Frank Kite's proposed region, and we go right here. So we probably do have a CM carbonaceous chondrite. And in addition to that just being a phenomenally cool aspect of the impact story, you're able to look at a fragment, even if you haven't identified that fragment, and say, this is of cosmic origin, and almost certainly this is related to the bolide that hit at the end of the Cretaceous. That's amazing, it's phenomenal. Then, if you're able to actually identify it, and we're on the road to doing that, then you can actually say, amazing, we know what it was. But it's not just cool, that actually has some significance, because when that asteroid came in, you're looking at a 10-kilometer diameter piece of rock. The composition of that rock is not trivial. The composition of that rock, when it was vaporized and went into the atmosphere, contributed to that atmospheric perturbation. That contributed to whatever happened to Earth's biota. So knowing what that composition was it high in sulfur, was it high in something else, what actually went up? You can combine that with what you know about the target rock and have a better idea about the dynamics of what occurred on the day of impact and why the things happened the way they did. So this is an important step forward in our story of understanding about the entire impact event. And one thing that we do know is the impact did not have a very good effect on Earth's biota. It was not compatible with life. It led to the massive extinction. I'm going to go through these very rapidly. A couple of high points about this pterosaur. Again, this is the first pterosaur embryo from North America, the first one from the late Cretaceous worldwide, the first one from an Asdarchid pterosaur. There's a lot to learn from this. And also, we're talking about when did the impact hit? You know, the impact occurred sometime in the spring to summer months. You know, we actually just performed a study that determined that's the most likely range. And there are a whole bunch of vulnerabilities that are inherent to that time span that are going to occur. These things are oviparous. They do have precocial young, probably. How does that affect? Now we can actually postulate, well, you know, we can figure out different ways that could have been affected by the impact. We look at the Thessalosaur. Basically, we've got a dinosaur at the KPG boundary. It closes the gap. Usually you don't find dinosaurs right at the KPG boundary. You've got a significant gap. This closes that gap completely. In addition, we've got details about that particular type of dinosaur that weren't available before. And this could have been killed by the impact. That's some significance right there. Very, very interesting. And also, if we do histological studies on the bones, we can work backwards and find out what things were like leading up to the impact in the environment, because the growth lines in those bones give us a record of that animal. And then, of course, the fragment. There's a beautiful EDS map of one of the fragments inside the spheral. And of course, that fragment is going to tell us more about the dynamics of the impact event, what the asteroid was made of, and possibly how it could have affected life on Earth. And this gets us so excited because we know the asteroid caused the extinction at the end of the Cretaceous. To see a piece of the culprit is just a goosebumpy experience. And lastly, the story that's kind of brought forward about this whole event in the Cretaceous kind of comes full circle. It's not just about the late Cretaceous. It's not just about what happened back then. It relates to today as well. The mode and tempo of the extinction event is very, very similar to what we see today. The rapid damaging effects to the ecologies today mirror, to a startling extent, what we see in the fossil record for how fast the extinction event occurred in the Cretaceous, much more so than the other mass extinctions in Earth's history. So that is a startling thing. And obviously, it's up to us. We have the capability of doing something about that and learning from the fossil record. And it is indeed the fossil record that is our way to learn how to do something about it. We are the only species on Earth that's ever been able to learn from this. It's up to us to do it. And the fossil record is our way of looking back into that window of time and actually seeing, how do Earth's biota, how do these animals and plants, how do they react to a global scale hazard? It's not a simulation, it's not a question mark, it's not a hypothesis. You're actually looking through time at the fossil record to see what happens. That's our best way of understanding what's happening today, what could happen today, and how could we have an effect on that. So that's our obligation. And with that, I will thank the following individuals and all of you as well.
Thank you so much.
Thank you.
Thank you so much for your presentation.
Thank you.
I think a lot of you understand now that a number of us had trouble sleeping last night. These results are so exciting. I think you can say that these are some of the most significant results in our century to really nail down what happened on that day when we were struck by this tremendous, now better identified asteroid. So that was incredibly exciting. Thank you so much for your presentation. We will have questions and answers later, so we'll take a break now. Thank you. Hello and welcome to NASA's Goddard Space Flight Center. My name is Michelle Thaller and I'm here to host a question and answer period about some extraordinary findings about the day that the asteroid hit that made the dinosaurs go extinct. And we have Robert DePalma here, who and his team have just had some incredible discoveries. I'm still speechless, I have to say. There were so many things that when you were talking, we were just emotionally reacting to. People were, I saw Christa, she was nodding and she was going, oh my God. There was just amazing evidence today presented that you have captured the moment that asteroid hit, the ejecta came, seismic waves ripped through the planet, and some of these organisms were swept together and died. I mean, it's amazing to be standing in front of that right here. So this question and answer period can start many different ways, but one of the things that I wanted to begin with is that just putting the science aside for a second, there's quite an interesting personal story here for you too. Because as you began to look into this deposit, well, for one thing, I understand this deposit was thought of as kind of confusing. People didn't know what to do with it. And so a lot of scientists kind of didn't want to work with it, didn't seem very clear. You stuck with it, but your findings were controversial. And you got some pushback about it. Can you tell us a bit about that journey, about people being skeptical and now people being very excited about these?
Science is about being skeptical. You really have to ask questions and don't take anything on face value. That's what happened with Alvarez and everybody else when they first proposed that an impact occurred. Nobody agreed with it. And if everybody agreed with something, I'd be kind of worried. That's when people aren't really thinking critically about it. In this case, what you do, and what you do as a scientist, is you find what evidence lines up, what does it mean, and what does it tell you? You don't tell the story. The evidence, the fossils, the data, that tells the story. And the longer you work on it, and the more of all of those items you collect and you're able to interpret, they are actually forwarding that information forward. And in this case, all of the data, the information that different teams are putting together, our team is interpreting based on these specimens, all it's coming together to sort of support this rich story that is linked with the end of the Cretaceous, the end of that time of dinosaurs.
It's a very calm and very measured scientific response, I have to say. To me, it doesn't match the excitement I feel about this, the joy, I have to say. A bunch of us were just jumping up and down when we heard about this and what was going to be presented. So there's also an emotional story about, as you began to piece these things together, realizing what you had found. Can you take us a little bit on that as well?
When looking at the fossil record, usually you're looking at really long time scales, millions of years, tens of thousands of years. And really, as paleontologists, we are passionate about the animals. I am passionate about the animals and whatever was existing at that time. So whenever I'm able to look at something and kind of have a fossil in front of me and be able to tell what that animal experienced, what was its life like, what happened during its life, how did it die? That's a special thing because it gives you a window into that animal's life. There's one creature experiencing what another creature did. And in this case, all of these animals that are just tumbled together in this deposit sort of had what I like to refer to as a front row seat to one of the most magnificent events of the late Cretaceous, the impact event and its aftermath. And how did it affect them on an individual level? And that's just such a personal story. Each one of them would have experienced it a little bit differently. And to see that kind of develop in front of your face in the outcrop and in the lab is a really personal experience. You're there and you're listening to that animal's story.
There's something really immediate about this. I mean, I'm looking down on a specimen of a fish, And you pointed out to me that there are tiny little spheres of glass stuck in its gills. You know, this creature died, it suffocated, because its gills were clogged with ejecta that had to do with this huge impact, this asteroid hitting the Earth. And there it is right there. You know, these things, you know, had this, you know, they died because of this happening. Like we were talking about today, you're looking at this moment. And we were all just mentioning this even, you know, we were having lunch together today. This was a moment our ancestors also experienced. We are related to things that lived through that day. And of course, things changed incredibly. This incredible rich ecosystem dominated by the dinosaurs, you know, that went away, and this mammalian ecosystem begins to become, you know, more dominant. So we're looking at an amazing change. Maybe we wouldn't even be here talking about this if that event hadn't happened.
If you put your finger on a single point in time in the rock record and say that point was absolutely pivotal to the world, this was one of those points. Because you can literally get your finger and put it on the KPG boundary clay, the impact fallout, and say, that's your dividing line, that's your pivotal moment. Because you're absolutely right. The mammals rising up and being able to diversify, that massive shift in ecologies and ecosystems across the globe, they're tied to that moment, to that impact. And to see these animals that would have experienced that event, and then to look closer, like you say, and you can see some of the impact debris packed in the gills of the fish. So that fish interacted with the impact debris. The whole story is there. You've got the impact that caused that tremendous shift. You've got the animal that experienced it, and then you've got all of this in one layer that gives you a moment-by-moment record of the aftermath. You've got this layer cake of an incredible story.
So just to kind of give people a chance to start asking questions, we have with us Dr. Jim Garvin, who is the chief scientist here at NASA Goddard. I was sitting next to you during the presentation. You were reacting. You were really excited. At one point, you actually were almost like at the point of tears. What are some of the moments you remember that you were looking at the evidence thinking, wow, look what they have?
Well, I think what Robert's done with his team here is connect the way we looked at the history of the rock record on Earth as defined by life in these names of eras we all grew up with that became known as Cretaceous and Triassics and all that, to the record of impact. This life on the rocks cosmic collision story that we've already used on other worlds. How do we define the eras on the moon? We name them for the eras of impacts that define different time horizons. We've made a link now beyond our planet through the lens of the bigger universe. Robert's stuff now starts to give us data, I see, for that connection being expanded. So, you know, maybe KBG is the wrong name. Maybe it should be the big C for Chicxulub because it defined a change. And those connections aren't only at the big animal scale, as some of your findings, but also the microbial scale. And how we read those records, I can't wait to see what you learn, because my question is, you found preserved elements of this micro-comminuted impactor that made this event that changed the course of the history of life. If you played the tape backwards, we wouldn't be here, to quote a certain Yankee fan. So what do you think about those? I mean, that's a finding of cosmic significance. It's Mother Nature's best sample return to give us a little piece of what she did to change the course of life. I mean, why don't you tell us about that, Robert?
Well, to find any sort of material that's associated with the impact event and really well-preserved fragments, like the cosmic material we've got, it is like going back in time, getting a sample vial and getting material from the site of impact and being able to study it. And working out the dynamics of the impact event itself is incredibly important. That is paramount to understanding how that impact affected life on Earth and how natural hazards are going to affect global ecosystems. But it is a tremendously moving kind of a feeling, because you are literally connected to these moments in time that are better understood now, but still poorly understood in many different ways. And they interfinger with so many different aspects of science and life. So these questions are incredibly important to answer. And as the answers are kind of flowing out, each one kind of builds the excitement and then leads to more questions.
Well,
and speaking of leading to more questions, I mean, so there were people here that were paleontologists, Jim, that were asking you about meteorites. So where would this meteorite have come from? Does anything about the structure, the analysis they've done, does that give you any clue about the history, the structure of the meteorite, this kind of meteorite?
well, Roberts and his team showed us that this is a carbonaceous we think, from your preserved evidence, in those time capsules of amber within a spherule that was made by the impact ejecta. I love impact ejecta personally. It's very moving. Didn't want to experience anything like the gills on the fish, but nonetheless. So there is a little piece of those things that we're now going to sample what they tell us. We just completed sampling the asteroid Bennu. Not as big as the one that hit the Earth at Chicxulub, granted, less than a kilometer across. And we're going to bring back those materials to study in the way Robert is studying the impactor that made this cosmic event. So those connections to that part of the inner solar system that records that stuff, those artifacts of the collisional history of Earth, he's got it. So we're bringing it back thanks to robotic space flight. Wonderful job by OSIRIS-REx. And Chicxulub deposit a little sample of her own for us to study. And maybe other impacts. Other ones not as consequential, but equally interesting. Just in the last 40 years, understanding the role of impact in the history of life, climate, and all that is a profoundly new change that was heretical, as you said, Robert. It was, you got to be skeptical because everyone was telling you that's not the way it was. And so I think, your work is showing us what could really have been. And that's the way science works, changing paradigms.
So also with us, we have Dr. Christa Peters-Lidard, who is our Deputy Director of Science at our Science and Exploration Directorate here. And you're a hydrologist by training as well. So what are some of the things that jumped out to you?
Oh, yeah. Well, thinking about the storm surge, right? And the power of water, right? 10-meter high deposit. And just thinking about how what the bed load was like. There were logs recovered at the site. Just the power of the water in this event, and magnitude 11 or 12 earthquakes. It's just blowing my mind. So, one of the things that occurred to me is, you have these two deposition episodes, right? So, how did the composition change, from those two episodes, and what does that say about, the physics of the surge in those two episodes?
That's a phenomenal question, and that's one thing that we've been thinking about quite a bit. The sedimentary record is going to give you the details about that story.
Yeah.
And the grain size and the bed forms and everything else you get there, they're going to tell you what it was like if you know how to read it. And in this case, we had two pulses to that surge. There was one initial pulse, it backflowed, and then there was a second long pulse. And we know that they occurred right after each other because you have animals and plants that would have been very delicate that cross-cut all the deposit. So you're not going to have a long hiatus between those two pulses. And then when you look at the pulses, there's a little bit of a difference in composition. So the first one was much more turbulent. That first pulse had a lot of rip-up class, had a lot of sand content. The grain size was a lot bigger. So you had a much more turbulent surge. The second surge, more mud, more clay-sized particles, and it appeared to be a longer surge. So we had this massive, really bad turbulent surge, backflow, and then a longer, more protracted final surge before it slowed down and all the waters receded, leaving this veneer of mud and animals and logs and everything on the landscape.
Cool.
Long live the logs.
Yes.
We also have Dr. John Mather, the senior project scientist for the James Webb Space Telescope, and a physicist. So John, what's your take bringing the physics into this?
Oh my goodness, I'm extremely excited to see the evidence that we've now got for the details of what happened on that day, because this is the first chance we really have to check all the incredible calculations that people can do with hydrodynamics and simulations of computer versions of rock hitting the Earth. But I'm also led to think about implications for our search for life elsewhere in the universe, because, well, it was pretty tricky here. How much could we forecast? How could we predict? So if we're going to look for life on other planets, are we going to imagine that they're just sort of sitting there passively producing life? Or do we imagine that they also have a chaotic history with crashes and evolution and extinctions and disasters one after another of the same sort that we've had here? We've had snowball Earth, where Earth was frozen solid apparently. We warmed up. We've had huge changes, catastrophic to everything that lived there at the time. And here's one catastrophe we can examine in detail because it happened so quickly. But we should be picturing catastrophes everywhere that we're looking for living things, not just here. So look on Mars, look on Europa, look on Titan, look at the other places that are interesting as sources of life. Catastrophe everywhere. So, and you're thinking also, what does it feel like to be there as a living sentient creature experiencing that day, which is something people I don't think have fully appreciated, because you feel it and you see it. You think, I'm like an animal there. I'm feeling the heat. I'm feeling the water. And I don't think we've really been able to picture that part in the past. So thank you for making that so possible for us.
It's an absolutely fascinating thing, and you mentioned life on other planets and how catastrophe might play a role. That could also go the other way, in that the frequency of certain levels of catastrophe could have a positive effect in some ways, because those could actually spark different changes in the evolution of life on those planets. So in the short term, meaning in the million to 10 million years scale, it might not be so good for those that are experiencing it. But in the grand scheme, that actually can bring about different changes in the trajectory of those evolutionary schemes and bring about different innovations. So it's really fascinating to think how that interplay occurs.
And also just finding the evidence for it. I mean, one of the things that really, I worked on the Spitzer Space Telescope, which is an infrared telescope, and we would see events where there would be this huge blast of heat from a young planetary system. And really the only explanation was that two planets had collided. And that was something that seemed impossible. But then when the lunar samples were brought back from Apollo, there were possible clues of that having been the origin of the moon. We wouldn't have even known what could have happened in an exoplanet system had we not been to the moon to get that sample. So, I mean, the tremendous cataclysms that drive the formation of planets, the evolution of life.
Well, and Goddard thought that the small craters on the moon were volcanoes.
Right.
And described them in is motivating some of his work, leading to the rockets, the early fueled rockets that led to what we have today. Didn't realize that the mare were impact basins that bespeak what Robert has shown us here on Earth can do to a life-bearing system. So I think that's stunning. We're becoming aware.
Yeah. And then finally, we also have Dr. Gavin Schmidt. He works for the Goddard Institute of Space Studies up in New York, and the director, I should say, not just works there. But we were talking a bit earlier in the day, and you had all kinds of questions that were coming into your head about what would the atmosphere have been like? How would the chemistry have changed? What are some of the things that stood out to you here?
So I'm very interested in the climatic impacts of this. So I mean, we've talked about the instantaneous impacts. The fire from the sky, the impact, the earthquakes, the seisures in the water. But some things will have survived that, but they might not have survived all the other things that came afterwards. So what happened to the carbon cycle? What happened to things in the stratosphere? How long and how deep was there an impact winter? Was it warm, then it got cold, then it got warm again? What happened to the carbon dioxide that was released from all the fires? Was that the cause of the acidification events? And I think we haven't really been able to kind of piece together that history in very much detail so far, because we haven't had, specific information from the time event itself, which I think this is going to help with a lot. But we also haven't had the models or the understanding of how all those things fit together, particularly in the Cretaceous context, for us to be able to do that. So really, it's only in the last 5 or 10 years that our kind of global scale models have enough physics to be able to answer these questions. And then this information coming in kind of really primes the pump for, I think, future explorations of that whole series of cataclysms, right? Because you've got the impact, but then you've got the winter, then you've got the starvation, then you've got the fires, and whatever order, and maybe, there are some places that were refugia. Maybe there were some places that were not affected by some of these things. And maybe we can learn a little bit more about, that just even the short-term changes that occurred. And like climatically, it's the same processes that, as you say, that we're changing now through a different mechanism. Changes in carbon dioxide, changes in ocean acidification, changes potentially in stratospheric input if we ever decide to geoengineer our way out of this. All of these things, the extinction events, all of these things have parallels to the impact event, but also to some of the other kind of interesting events that happen in the Cretaceous or in the Eocene. But it's a fascinating tableau for us to be able to build credibility in our understanding of what's happening now by explaining what happened then.
I couldn't agree more, and I couldn't say it better than you just did. I absolutely agree. And adding to that, you're talking about all these different processes that occurred afterward, and you're talking about injection of different debris into the atmosphere. Every little tiny step forward, we're going to add more data to that, and by we, I mean the whole scientific community, and that makes that a more complete picture. And part of that is, if we do have these pieces of cosmic material, by ascertaining what they're made of, what's their makeup? That's what's being injected into the atmosphere along with the target rock. So that's helping us to better constrain what was being put up there. And by studying other things at the site, including the KPG boundary that's capping the deposit, we're working on kind of constraining how long that impact winter would have been, how long would the blockage of sunlight occurred. And we're actually kind of fine-tuning the previous data that's been collected on that. So hopefully that gives us some really interesting numbers. But obviously, all these factors come into play of how these poor things had to weather those first years, 10 years, 100,000 years, whatever it was. And that applies exactly like you said to today.
Yeah, I mean, like you mentioned earlier that there's some evidence that this happened in the Northern Hemisphere spring, right? That's kind of interesting, right? Because the impact itself is quite close to the equator, but in the Northern Hemisphere. And so what does that mean for how much this debris spread across the hemispheres? Maybe in the Southern Hemisphere, things were a little bit different and maybe not so dramatic. I mean, there's a lot of things to explore by looking at the details of what's coming out of these new studies.
Think as well about the trajectory of the impact and the angle of impact of this bolide. There are some impact angles that are incompatible with any fragment surviving the impact event, and there are some that are somewhat compatible, and there are some impact angles that would lead to a much better likelihood that you would find a fragment. So the fact that we do have a couple of fragments kind of helps us to constrain that a little bit better. I know there have been a bunch of different ideas put forward in the past. This might help us to kind of weed through those a little bit better and have an idea of what that impact angle would have been. And of course, in turn, the angle of impact has its own set of implications in itself.
I think one of the sidebars of what Gavin and he was saying is, so we think by theoretical physics that this scale of impact, 10 to 20 million megatons of TNT equivalent, would have mostly blown off the Earth's atmosphere as it existed at the time. It's all gone. What happened? It obviously didn't do that completely because life persisted. You have the post record in your stuff. So what was the early time like? Because, we're also dumping gigatons of stuff into the stratosphere, mostly from the target, which was a carbonate bank with ocean waters and all that. So that's the primary load, not the impact. That's a little thing. It's excavating to 30 kilometers in the, quasi-oceanic crust. Holy crap.
They get 30 kilometers down?
Probably.
The transient crater.
Absolutely. So, oh my God. I mean, now we're through the skin of, not the continental crust, but the oceanic crust, be right through it. Yeah. So, God forbid, what does that all mean? And these are the implications of that early time life record and the chemical record that you were getting to. If any of that's preserved, those are going to be those model constraints that we can use for models that, that can produce where everything's going, but what else is going on,
If it got down that deep, did it actually was that like a volcano? Did it hit magma or something?
Well, it would have hit whatever's at the 30 kilometer depth in the transient cavity propagation, like Robert said. But then the excavation stage moved this massive stuff out and rippled it through over a period of a few hours. And the resonant thermal pulse was probably, thousands of years in that region, in that area. So that relic scar is going to be part of the Earth history in that region. You're 3,000 kilometers away, so that's a great place to look at the consequences without having been, eradicated quickly, or more quickly than you'd like. probably didn't feel a thing.
Well, I don't know if anybody likes to be eradicated.
Right. No eradication.
Oh,
Sorry,
yeah.
Robert. Eradication is not.
Yeah, that's not a good thing.
Well, actually, and Christa, as a hydrologist, we were talking about how there were freshwater animals and saltwater animals all mixed together.
Yes.
So this really was a catastrophic flow of a saltwater body into a river system.
Yes, exactly. So, I mean, that was such a compelling piece of evidence here, right? That, you know, that you see these species together that shouldn't be together. And, you know, again, like, it made me, you know, curious about how, I mean, it was sort of a jumble of, of lots of things together. So, I mean, as you approached this jumble, you know, and you started to say, wait a minute, that shouldn't be here. Like, how did you approach, you know, going forward once you started to realize, like, wait a minute, this is different. This should not be here.
Well, before there was anything involving the impact, even in our brains, the two real red flags are, okay, you've got a river that would normally run somewhat east, and it's running westward now,
Right.
based on the flow direction. That doesn't make any sense. And you couple that with the fact that you've got marine fossils there, microfossils. You've got dinoflagellates, you've got foraminifera, and then you've got ammonites and other things, mosasaur pieces and marine fish, and sharks' teeth. You've got all those marine fossils mixed in this deposit that was created by a westward flowing surge, and obviously it's not supposed to be that way.
Right.
That's not the way rivers usually behave. So it's an exceptional event. That got us thinking, what the heck went on over here? Why did the surge occur?
Yeah.
And then we were finding ejecta and different things that connected it to the impact, and then there was the cap of the KPG clay. We're like, oh, it's that.
Yeah, yeah.
I bet you reacted more dramatically than that. I mean, you're talking about wanting to be in the minds of these creatures. I want to be in your mind as you started piecing this together.
Right, like,
oh
my gosh.
That was a
This
wild
could be
place.
it.
It was a wild place.
Yeah.
I can see the
wild.
parties.
So did you
Yeah.
find this site, or was it found and mapped, but people didn't really know what it was?
The site is actually a really incredible story, and it's actually a beautiful situation of how things really should work, of people working together. I worked on a site for my master's thesis that dealt with really fine time scales in the fossil record, and we wanted to find one closer to the KPG boundary. And there was a group of avocational fossil hunters who have a company that digs up and sells fossils, paleo prospectors, Steve Nicholas and Rob Sula. They originally set foot on the site, and they saw all these fish poking out of the site, which was a big red flag for them. You don't see fish in the Hell Creek Formation. Before that site, there were, I think, 3 or 4 articulated fish. It doesn't happen. The preservation bias is against the preservation of fish like that. So that was exceptional. Oh my God, we've got fish at the site. Little did we know that we'd be, wowing over everything else later. But that point, it was the fish. And they thought it was a lake at first because of the striations. And that was interesting to me. And they facilitated the work to move forward to my research group. And that's the best thing that could ever have happened, because we were able to piece together everything that occurred thus far in our research. And we were able to get all of these specimens, preserve them, because the environment out there is not conducive to the preservation of fossils. They're imperiled every moment they're in the outcrop. They will get washed away. The winter is bad on them. So that whole situation ended up culminating in a tremendous research project and an amazing interpretation of the site, and data that is now able to be used by God knows how many people to try to put the story together. So yeah, that one group actually first set foot on the site. And if they hadn't done that, who knows if it ever would have been found, because there were other people, researchers working in that area for decades, and they never saw the site. They never even found it.
They knew you liked fish, and so they were like, hey, here's something cool. Just look at this fish.
And look what history made for us. It goes from fish to putting together little tiny details of this massive story of the end of the Cretaceous. Who would guess?
You're talking about the data and all that. I mean, you guys are all here also. I mean, collaborate. I mean, what would you like to get from this group, and what would you like to get from NASA that'll make things even better, the story even more interesting? I mean, can you guys think here at NASA, the stuff that you'd really like to get a hold of that he has?
I mean, not physically, but I mean, we discussed just earlier, you know, what else is in those spherules, right? I mean, if there are air inclusions that can give us hints of what that paleo atmosphere was like in terms of carbon dioxide levels, methane levels, you know, I mean, just like in an ice core, you know, we preserve these bubbles, you know, that go back 1 million years. Okay, this is another level, of course. But if there is air that can be analyzed, that would be a huge input into what we're doing. Because we know that, you know, at that period, right, you know, the kind of end Cretaceous time, climate was changing. Even before the impact happened, there were climate changes, and you know, Cretaceous was a long period. There's lots of other things that had happened in the Cretaceous, the ocean anoxic events, and you know, the peak Cretaceous times. But there were things happening right then that we don't really understand. You know, was it related to tectonic changes? You know, closures of various seaways, the Tethys Sea in Europe. You know, it's unclear, and so there's a lot of focus on what was happening immediately before the impact. But then to have, you know, like examples that could really kind of ground truth some of those speculations would be of enormous interest. And then you have the things that could evaluate how well our simulations are working, right? So, you know, so we put in these assumptions, we run these models of various kinds, and you'd have to kind of string them all together, you know, kind of one after the other. And then, you know, okay, well, we predict this might have happened, or this. Tell us from the data which one it was, right? And then we can kind of constrain things coming back. And so those kinds of things, like, you know, things like temperatures, things like, you know, water isotopes, you know, all sorts of, you know, you know, how much burning there was, how much charcoal you find. Those are the kinds of things that are really key for evaluating our kind of suppositions.
It's going to yield more than that, right? I mean, you don't have all of the little bits of amber that you're going to find these things in.
Exactly.
That site has, we've only seen the tip of the iceberg. Only the tip of the iceberg. Every single season that we go out there and that the other research groups from other universities join us out there, something is found that we've never seen before, and it carries the research forward. And we were just having a conversation before about non-destructive analyses. I can think of a whole host of things that would be amazing for collaborative work on the non-destructive analyses on the ejecta and the other items here that would offer volumes of data. And with the hydro modeling, in terms of better modeling of the dynamics of the surge wave, that's something that is an amazing project that could probably lead to multiple papers, you know, down the road.
And I think there's another aspect, which is, Robert's already talked about it, which is, you know, this is one cosmic event recorded in Earth history with all the climate and other implications. But there's others. I mean, recently the Hiawatha structure in Greenland was age identified as being relevant to this transitional period of time, you know, into the PG, the Paleogene. We have others where there were mass extinctions observed of different magnitude, the Eocene, Oligocene at Puppy Guy, the Permo-Triassic further back. These are the Earth record as the chronology of the solar system that we use relative to the moon and other chronometers. This is critical for planetary sciences. So I think Robert's data and materials can be analyzed through some of those techniques he mentioned, which we're now using on lunar rocks, some of which have been, you know, stored away for 50 years. So we have the better tools. So that cross-disciplinary collaboration, I think, would be very fertile. And I have a question for you, which relates to that, which is, so what about the pollen? You've now got amber, you've got spherules, you've got pieces of the impacting object. Then there's pollen, which is a very good indicator of many aspects of environment and a really robust one in the Earth history. You've talked about it a little bit, but maybe that's an area of very exciting sample analysis.
And it's underexplored right now, too, because the pollen so far, yes, it exists at the site, beautifully preserved. And thus far, it has been explored mainly as a biostratigraphic marker. So we're establishing where we are in time. But in terms of working out the biota back then and the turnover of the ecological turnover and what happened right at that moment and then up into the lower Paleogene, that hasn't been done over there yet. And it is ripe for the study. So I was going to ask before, when do you want to get started? But you know, with the pollen too.
I think
honestly,
Gavin's ready. We're all ready.
But it's, John, yeah.
So I'm ruminating on, this is like the archetype of hands-on research. Whack, whack, whack with your tools and dig in a little bit into the rock and see what you find. And if you're lucky, you notice that there's this little brown layer and you realize it's a dinosaur skin and you're really super careful. But I keep thinking, isn't there something high-tech engineering could give you? And I don't know what you need, but I sure think it's worth finding it, whatever it is, because this is so important and it's so precious. And there's no other site like this in the entire planet that we know of. So we need to get everything we can. And so before it all washes away, let's find it and let's give you all the help we can possibly imagine.
I'll never try to turn away any really, really, really good recommendations on that end and putting on the thinking caps, because you're absolutely right. With the fossils and their mode of preservation they're very fragile, they're almost impossible to prepare and to stabilize. We have had to develop new techniques in excavation and stabilization for these that are different than what you normally use in the Elk Creek Formation. They dictate that we have to do that. And basically through that process, we have developed incredibly, painfully detailed excavation practices, going centimeter by centimeter, and then stabilizing as we go to accomplish this. But we're always trying to up our game, and we are always trying to refine these methods and find better methods and really think outside the box. We recently got some of the specimens that were almost impossible to move because you put plaster jackets on the matrix, but if that is saturated with moisture, you can't move it. It's going to be basically the consistency of peanut butter. It'll get destroyed. So what do? You can't put glue on that because the glue's not going to go. It's already saturated with something else. So we decided, okay, we'll use whatever it's saturated in, which is water, to then stabilize it. So we flash froze this block with liquid nitrogen, turned it into a solid block, stabilized it that way, moved it out, and then we thawed it in a controlled environment before research. And we determined via SEM analysis and thin sections that was not harmful to the fossil. So we need a lot more thinking outside the box like that. And it's not just going to come from us. So
We do a liquid nitrogen factory on site.
No, I was thinking about Jen.
We had liquid nitrogen, John.
We
involved in a
got
certain
liquid
telescope.
nitrogen.
We know how to do that.
I was actually thinking about Jen Eichenbrode's work on stabilizing organic compounds, which is useful in the Mars analysis. I mean, in that case, you're basically going molecule by molecule to stabilize the sample. That's something people do here.
that would be absolutely useful. Absolutely.
Also, the new classes of tomographic imaging at outcrop scale that are now being used in certain sectors, including in geophysical exploration, could image at centimeter scale in a three-dimensional volume into a target, depending on wavelengths of, that could characterize your site before you've actually dug into
The
it.
astrobiology group, I think, needs to
Would be
contact
very helpful,
these
yeah.
people. Yeah, absolutely. And speaking of astrobiology and stuff and the search for life outside, so I mean, Jim, understanding impacts like this here, how does that help us understand other planets better? I know that's something you think a lot about.
Well, I'm just struck because on Mars and Venus, we have Chicxulub-class impacts in the more recent eras of their record. And we use those on the Moon to characterize whole time blocks. We see them on Mars. We wonder about them in this, more recent historical period of Mars as not something from Gale Crater 3.5 billion years ago, but something from the last billion. And then there's Venus, where there's only one in this size class, maybe two if you get sketchy. So, wow, what if Venus did, as some climate models suggest, done in fact at Gavin's group, have persistent surface waters for billions of years? And that suppressed the record of impact, and the only ones we see are those that happened later, that are more recent, that are the Chicxulubs of Venus, or other worlds. And that's just thinking of Mars and Venus because they're climate-relevant objects nearby. And exoplanets, where John's telescope and others will be able to start ferreting out those classes of objects, that might have reflected an impact-preserved aspect of atmospheric change. Unbelievable, the connections. And so we need Earth ground truth to apply that message forward. And you've done that. And I think we can learn from you.
And we can continue doing it forward. I
Right,
mean, yeah.
right. Yeah.
Not just me, it's a massive collaborative
Massive
effort.
collaboration. Lots of women and men working on this. It's all good.
I think we've got a plan going forward.
Yep.
And I guess, anybody else want to say anything before we wrap up our discussion?
When can we visit?
What an incredible day. That's right. Well, we'll start making plans right now.
It's mushy right now,
Oh, it's mushy, okay.
and that's the technical term.
Right.
But the sky's the limit.
Yeah.
Let me know when.
With that, we'll wrap it up. Thank you so much for joining this on this exciting day here at NASA's Goddard Space Flight Center. Thank you very much. Thank you.